Right. Hi, so I'm Shasvath Kapadia. I'm a postdoc in the Astrophysical Relativity group. And this project, whose title is put over there, is a work that is done with Aditya sitting there and Ajit over there. All right, so the key point here is that we want to be able to constrain the time variation of Newton's gravitational constant using gravitational waves. There's motivation for this. This idea that Newton's constant could vary with time is not new. It was first proposed by Dirac, I think in the 1930s, where he basically argued that if the universe is expanding, then it should somehow alter the strength of gravity, and in turn, it should cause the gravitational constant to change with time. Now, since then, there have been a number of alternative theories of gravity that basically predict this, and therefore, there have been efforts to try to constrain this time variation of Newton's constant using experiments. Now, there are a whole range of experiments that actually do this. They involve the cosmic microwave background, galactic binary neutron stars, helioseismology, etc. And in fact, I think the strongest constraint currently comes from lunar ranging. But what is missing, at least in this list, is a constraint based on gravitational waves. Here I want to point out that even with gravitational waves, there has been work done in constraining the time variation of Newton's constant. But the current value of the upper limit on this time variation is very weak using gravitational waves. I put down this value over here. G dot over G naught is less than 10 to the 5 per year. So clearly, it's a very weak constraint at the moment. And the reason is because the current method that attempts to constrain this time variation actually looks at only the time that the gravitational wave signal spends inside the frequency band of the detector. And for LIGO type detectors, this time is of the order of a few minutes. So it is not at all surprising that G dot has been very weakly constrained using gravitational waves and the signal that lies in the detector's band. What we propose to do is to once again use gravitational waves from binary neutron star systems, but hopefully put much stronger constraints, several orders of magnitude better than what is currently available from gravitational waves. So I'm going to now spend some time trying to explain what the method is. I'm sure everyone knows what gravitational waves are, but just in case, gravitational waves are ripples in the fabric of space-time produced by time-varying mass quadrupole moments. Specifically, compact binaries, not just binary neutron stars, compact binaries in general have a time-varying mass quadrupole moment, and they produce gravitational waves that are actually detectable here on the Earth. So these gravitational waves produce strains in the detectors, and the signal, once it has been actually detected, looks something like this. So this is a typical gravitational wave signal. You have the strain amplitude as a function of time, and you have this typical increase of the frequency as a function of time referred to as a gravitational wave chirp. Now, the very nice thing about gravitational wave signals is that macroscopic properties of the compact binary actually imprint themselves onto the waveform. So what this means is that if you could actually detect the waveform, and if you know the shape of the waveform, you can infer what the masses of the compact binary is. Now, for our purposes, though, there is one slight problem, and the problem is that the masses and Newton's constant are completely degenerate. Now, typically, this is not a problem, right? All you do is you fix Newton's constant to the value that you know, and you infer what the masses are. But for our purposes, we actually want to know what Newton's constant is at the time of the coalescence of the binary. So we need to be able to come up with a way to break this degeneracy between the mass and Newton's constant. All right, so the method that we use to extract the signal from the data is a method called matched filtering, where you take a template of the gravitational wave signal and you cross-correlate it with the data. This produces a signal-to-noise ratio. If the template perfectly matches the signal in the data, then you will get a peak in your SNR, which is typically suggestive that the signal represented by the template exists in the data. Now, if supposing the gravitational wave or the gravitational constant at the time of coalescence were different from the gravitational constant today, And if we used in your template the gravitational wave constant, the gravitational constant today, what you would end up with is a biased estimate of the mass of the compact binary. And this bias factor is basically put down over here, G coalescence divided by G today, okay? So the true mass is M coalescence, and M naught is the mass that you estimate, okay? Now, there's another interesting point here, and this is where we are going to try to break this degeneracy between the gravitational constant and the mass. And the point here is that for neutron stars, the mass at the time of formation of the neutron star goes as G to the minus 3 by 2. Okay? So this is an important point. And this is something that you can check from your TOV equation, which is supposed to be the equation that represents the neutron stars. And once you have an equation of state with the TOV equation, you can get your mass. But regardless of your equation of state, this is always true. Okay? So now I come to the main point, which is equation 4. Now, supposing you do not assume any change in the mass during the inspiral of the compact binary, then the mass at the time of formation should equal the mass at the time of coalescence. That's the first point. The second point is we are going to make an approximation. If supposing the inspiral duration is much, much bigger than the time it takes for the gravitational waves to get from the location of the coalescence to the Earth, then what equation 3 and 2 give you is basically equation 4. Okay? Now, just to elaborate on this particular approximation, from studies, it can be shown that the inspiral duration is of the order of billions of years, whereas the gravitational wave travel time, specifically for the binary neutron stars detected by LIGO, is of the order of 100 million years. Okay? So clearly, this statement is true, and therefore, this approximation should hold, all right? So what this means then is that if supposing you were to detect your masses and you have a theoretical limit on what the masses should be based on the TOV equation, if the detected masses fall outside the range of the theoretical range, then this is an indication that the G at the time of formation is different from G today. So that is the central idea of this method. Now, what we can now do, because we want to put an upper limit on G dot, not just the variation of G, we can put a strict upper limit by assuming that the travel time of the gravitational wave is the time that it took for the G formation to get to G naught. Okay? And this is the result that we get. So this is the constraint on the variation of G. And what I have over here are, you see this gray shaded region? So these are basically the upper and lower limits on the masses, assuming that the TOV equation is correct. And as you vary G, these upper and lower limits on the masses will change. What you see in this pink band, you have a darker shade and the lighter shade. These are basically the mass posteriors. So these are the mass distributions that you have acquired from gravitational wave data. So the darker color shade corresponds to the mass of the heavier of the two components of the compact binary, and the lighter shade corresponds to the lighter of the two components of the compact binary. Okay? So from here, we can actually put a constraint on the time variation, putting the strict upper limit that I talked about before, which is the travel time of the gravitational wave from the source to the Earth. And this is basically the result that you get. So for the first binary neutron star coalescence that we had, GW170817, these are the constraints that you get. If the numbers are not clear, the constraints are of the order of 10 to the minus 9 per year. So many, many orders of magnitude better than the previous gravitational wave-based constraint on the time variation on G. Using the next binary neutron star detection that was recently made public, which is GW190425, this has larger masses, but more importantly, it's actually further away, so your constraint gets even stronger. I think it's still of the order of 10 to the minus 9, but it's a stronger constraint by a factor of something like 4 or 5. I have put down other constraints for comparison. Like I had mentioned in the beginning, the lunar ranger-based constraint is the strongest. But this work is interesting because it puts the strongest constraint on G dot based on gravitational waves alone. So this is pretty much the summary of the work. Hopefully this work will be published soon. And if you have any questions, I'll be happy to answer them. Yes. Oh, sorry, is there an easy way to understand it? Why G goes as, well, I'll confess here, what we did was we looked at just the TOV equation and we looked at, we did a dimensional analysis. And then we also looked at several equations of state and we basically varied G to see what mass we get. And we always found that the mass goes as G to the minus 3/2. But I don't know off the top of my head whether there's an intuitive way of seeing why the mass should go as G to the minus 3/2. Do you?
Comes directly from the dimensional analysis.
Yeah, that's
you can
what,
just
yeah.
no, the alpha is not dimensionless. The alpha is not it's proportional to G power minus 3/2 is what is the claim that you can make.
Okay.
Mass will be proportional to G power minus 3/2.
Oh, so, okay, maybe, yeah, this is an important point. Maybe I actually skipped over this. So this alpha basically captures the nuclear properties. So what we are assuming here is that the nuclear properties don't change with time. It's only the gravitational property that changes with time. Okay, that's an important statement I should have made. So.
Can't one estimate in these cases the mass from the electromagnetic signals, let's say some...
That's a great question. Actually, when I first come up with the idea, I actually pushed forward in that direction. But then both Ajit and Aditya pointed out that it is true that you can do it, but the models are so uncertain at the moment that in fact the constraint that we would have got in terms of the error bars would have been much bigger than this method, which is why we eventually switched to this method. But absolutely, that is a way to do it, yes.
So maybe this is a naive question. So the mass of the star at formation time, right, apart from this G dependence, it also depends on many other things. Right?
That's right. Yeah.
So, but then how do you really make a prediction of what, like, what the mass should have been?
So, okay. So what we are arguing here is that whatever those other things are, they are purely nuclear. And here, this is clearly an assumption that the nuclear properties will not change as a function of time. That's the assumption. And the second assumption, of course, is that the TOV equation is true. This only works if the TOV equation is true. This comes from the TOV equation. If the TOV equation breaks down, then this method breaks down, right? So.
But it's shown in this gray region. So we don't know alpha, but we know some bounds on alpha. Well, we know the minimum possible mass of a neutron star and a maximum possible mass of a neutron star, assuming a value of G.
So the variation is alpha is captured in that mass range. I think that's what he's thinking. Okay. Yeah.
If we have no more questions, then
that vertical line is that shows the possible range of masses of neutron stars due to the uncertainty in nuclear physics.
okay. So if there are no more questions, then we would thank the speaker again. And